Greetings to one and all. Again here from the SEAM studio. This time around I'm going to have a look at the next in the series, the helicopter series aerodynamics, hazardous conditions and recovery actions. And note here it's going to be the vortex ring state. Now from time to time I'm testing people and then I hear the stories about how instructors out there are busy trying to teach how to recover from a vortex ring state, and then I get a little bit, it's like listening to some horror stories, because remember, if your recovery action is not founded on the aerodynamics, or the pure aerodynamics for that matter, you might just come second with the recovery. So there are weird and wonderful ways of getting out, and as I say, it's like Heimlich maneuvers out there, and I'm not going to mention all the names or who's in, but let us go and have a look at what the aerodynamic books will lead us on how to do this. The first thing obviously is to make sure, what's the definition: an unstable condition of flight where the blade angle of attack is increased until extensive blade stalling is experienced due to recirculating air, and that's the one that is important, resulting in excessive rate of D, and when fully developed can lead to total loss of control. Right, so in other words, if we look at the definition, it's an unstable. In other words, there will be random pitching, yawing, and rolling taking place as the aircraft is descending. Okay, let's just get past all these random yawing, pitching, and rolling moments, because very few of us has actually been into a fully fledged vortex ring state. So let's just look at the beginning of the vortex ring state. It is where you would have a vertical descent, and normally how it's demonstrated is once you've settled into the rate of descent, and the rate of descent is around about 800 feet plus, and you slowly start increasing the collective, you can actually see the rate of descent increases. Right, so that's the one that we're going to talk about. Now, why is it increasing? Obviously, there's air that's circulating. We are descending right into the air, and we will talk about the blade stalling condition. Right. It looks at the symptoms of the vortex ring state. If the vortex ring state is allowed to develop, a very high rate of descent occur. Right, we've said now, very high rate of descent. Where will you see it? Well, on the VSI, nowhere else. Secondly, in the incipient stages, in other words, the beginning stages, can be identified by increased rate of descent with power on. Oh my goodness, all right. In other words, we are not descending as in an auto rotation. It's power on, but still the excessive rate of descent is definitely visible. This will be accompanied by the increase in vibration and random pitch, roll, and yaw. Now, the vibration part is the part where everybody struggles, because all of a sudden we're sitting there and the aircraft starts vibrating and you actually think that you're in a vortex ring state. And now, well, if you think that you're in one or you're really in one, you're going to take recovery action. But if you take the wrong recovery action, if the recovery action is based on the wrong aerodynamic information, because this is what it's all about, then you might actually increase the chance of having an accident. And in fact, many a game pilot has actually sat outside ground effect in the hover, let's say around about at 100 foot. All of a sudden, they feel the shaking and they see the rotor RPM is low and they're in a vortex ring state. Doesn't matter whether you're really in it or not. There's only going to be one very correct. Okay, I shouldn't have said very correct. There is only one correct way. The rest, maybe, if, under, blah, blah, blah. But from an aerodynamic point of view, we will go through the lesson, you'll see this is what you have to do. Right, the recovery action must be taken at the stage because recovery from a fully developed vortex ring state, look there, it says there, a fully recorded is not necessarily possible, okay? May not be possible because the response is restricted. So the recovery actions must be taken at the stage because the recovery from a fully developed autorotative state may not be possible due to control response that is very restricted. Okay, so remember at the end of the section we're saying that it is important to recognize the symptoms earlier on, and when we have symptoms that's vaguely in this area, apply the recovery, and we'll get to that. Need and application of vortex ring state knowledge. There it is, the knowledge. What is that we do? All right, let's look at the first one, game work. Okay, let me enlarge it a bit. Game work, hard maneuvering coupled with pilot-induced rate of descent. Ooh. So when is it possible to get this? When you're doing game work, you're doing hard maneuvering with your helicopter, and there is a pilot-induced rate of descent, obviously with the speed too low, and so on and so on. So let's have a look at the functions. Hard maneuvering onto a downwind position ending with low speed and a high power required slow. If the speed is very low or very slow and you've got a high power requirement, I mean, you are setting yourself downwind. I've been there, and I can tell you it is just by the grace of God that I'm out of that one. But then I was lucky there was a runway in front of me and I could actually do a roll-on with the Alouette 3. So, you know, I had the facts of, let's go, it was favorable on my side. But in normal circumstances, well, I might not have been that lucky. Remember, everything at the end of the day will come down to how high are you? Have you got the potential energy to make use? And we'll get to that one. All right, tight circuit, from into wind to out of wind. You know that we do the tight circuit, and you know when we've got the right opposite, you can turn very sharply to get right onto and stop on it. Now, if you end up at out of ground effect condition, that is the problem that we're talking about. So be very careful that when you're doing hard maneuvering to end up out of wind. You don't want the wind on the tail now, because you're sitting with huge attitudes of the aircraft in that stopping maneuver. You're sitting with a lot of power, you're downwind, you're really just setting yourself up for trouble. High rate of deteriorating speeds in transitional phase or below. This is one thing that we've been talking about a lot, and if I just grab the helicopter here, remember when you do a rate of descent, and that is below transition, and we'll have to talk about what is this transition speed, we'll get to that. Below that speed, you want you want to try, you have to keep your rate of descent in the region of 300 feet. Here, you will be forgiven up to 500 feet. When it gets to about 800 feet, there's going to be no more forgiveness. So remember, this is not a game. You have to know where you are, and you have to know the consequences of what you're doing so that you can apply the remedy well in time. Insufficient power during out-of-ground effect hover. This is an absolute classic. Come in, out-of-ground effect hover, busy with something else, looking around, doing your thing, and the next moment you hear the hooter screaming, the main rotor RPM is drooped, the aircraft is shaking, you're in a rate of descent, and now power loss due to any factor in the hover, especially out-of-ground effect hover, and hover in the lee of a mountain or strong winds. In other words, if you look at insufficient power as a concept, this is one of the things that traps us into believing that we've got. Difficult one to say. All right, you believe that you're in the vortex ring state, This is maybe the incipient stages, or let's say it is the incipient stage. It's not fully fledged yet. But this is, if you can recognize this, the great thing about all of us is there's one way to recover. Not all the other nonsense that's floating around. One way. Just do it and you will recover. Downwind quick stop. Ooh, this one. I tell you, it's one of the favorite tricks. I do a test with somebody, we're flying around, and I say to him, okay, quick stop, go. And then they do a quick stop. I say, hey, but we're doing downwind at this stage of the game. You cannot just whip it into anything just because Charlie Murray or whoever said, you must do it now. Or you were doing game, or you were doing something, or you were flying with something and they say a jackal on the ground or whatever, and you do it. You can't. You must know where the wind is. Don't let anybody else trap you into going into the wrong side. Well, especially not me. Quick stop, where the rate of D is allowed to develop. This is one of the pet things. When we do a quick stop, go down on the power, maximum flare, then obviously the collective must start feeding in during that period until you get into the hover and a quick stop. During that period, if there's a rate of descent set up, I will not pass you on that specific exercise. I won't. I'll do another one, and another one, and another one, until you realize, or eventually I'll send you home. No. The fact is that the worst thing you can do is to set yourself up into the traps of getting yourself into the incipient stages of a vortex ring state. Very important one. So I think we must think about this one. But let's have a look at the intensification of the vortices. And the first one that I have there, I say, although the vortices are always present, I mean, that's true, it's always around the periphery. And when I'm talking about the periphery, there's always a recirculation taking place. Under certain airflow conditions, the vortex will stall, spreading out from the root to the tip. Okay, outwards, in other words. And as the stall spreads, because the angle of attack here is the highest, and as the angle of attack increases, more and more and more and more of the blade will stall. Right, so I'm not going into the aerodynamics, why it stalls from the root to the tip, but obviously by now you already know that. The condition is similar to in some ways to stalling a fixed wing aircraft, and when it's equilibrium is said to be in a state of vortex ring. Now I think the penny must start dropping. The wing is stalled. How many blades? They stalled. The disc now can be solidly stalled. Or stalled to sufficiently, in a sufficient way that it's not capable of being able to maintain the weight of the helicopter. Obviously, if there's any positive G maneuvers involved, then the power required is more, the thrust or the lift required is more, and so on and so forth. And then this state can be entered from several in-flight maneuvers, but the airflow conditions which give rise to its the formation remains substantially the same in all cases. And that is quite interesting, because the aerodynamic, the end of the aerodynamics will stay the same. That's why the recovery will have to be the same. Because it doesn't matter what you do. At the end of the day, the resultant of that, it says there, this state can be entered from blah, 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 which gives rise to its formation remaining substantially the same, and substantially, in the words used here, as referred to the AP3456A. If you haven't got one, try and get hold of one of those. Those are the aerodynamic books that can speak the truth. It means that we've definitely get a more than 50% vote, that it's going to be the same. Therefore, we've got a greater than 50% or a bigger than 50% vote, that the recovery must be the same. And that is then what we're talking about. So next let's have a look at the conditions to precipitate a vortex ring state. Well, there will be a few. The helicopter has induced flow passing through the disk as occurs in power flight. That's normal. All right, I don't have to speak about that one. There is recirculation taking place at the tip. When we descend, there's a certain amount of recirculation that's taking place, but the helicopter blades aren't stalled at that moment as yet. There's an external airflow directly opposing the induced flow as occurs for the high rate of descent, and this is the one where we're talking about now. Remember, if you've got a high rate of descent, there is a opposing flow. Remember, the airflow from here is pushing down, and you've got the air pushing up, effectively changing the relative airflow. And as this force increases, it reduces the Indo's flow effect on reducing the angle of attack, and it therefore increases the angle of attack until it stalls. That's what we're talking about in this one. It says there, indicated airspeed is low. That is a factor, so whenever with low speed, we've got to pay attention. One flight maneuver from which the vortex ring state can develop is when the helicopter enters a power-assisted descent with low airspeed. Other maneuvers where vortex, all right, power-assisted with low airspeed, remember? And that is why we say whenever we're looking at, for instance, you know, up to 40 knots, we don't pay it. That's still a good speed. But the moment that you're below 20 knots, you're entering into the area where it's very quickly going, where you're going to end up very quickly into the transitional stage. And in the transitional stage, this is where it's very susceptible to happen. Any speed higher than that, there is a forward flow. But if the forward flow has got no more real significance, then the opposing flow is the one that makes it difficult. As a result of applying power to recover from a low airspeed auto-rotation without first increasing the airspeed. A low speed auto-rotation, remember that in auto-rotations, and we're not covering it now, but normally the auto-rotations, most aircraft ranges anywhere from around about 60 to 70 knots. It's like a good ballpark figure. The magic number in helicopters are normally 40 knots, and there are various reasons why 40 knots is such a magic number. However, from a flare point of view in an auto-rotation, there are very little to no any effects left in the flare from 40 knots and below. Okay, you'll say to me, yes, a Robinson 22 has got no more flare effects from below 40 knots, but the EC120 has got a little bit. Yeah, I know that. Remember, we're talking about ballpark figures here, but the lower the speed, the less the flare effects would be. And the closer you are to the transition stage. And it would probably have been better if they said, when you get to your transitional stage, this is where the air is already upset, if I can put it in that way. All right, allowing the helicopter to lose height during a harsh flare. Now, remember when you're doing a quick stop, that's harsh flare country, not so. Downwind approach. And you would say to me, but who would be so silly to do a downwind approach? Guys, there's so many of us that helicopters are real working tools. We don't, in the operational area where we apply helicopters, we can't decide that the object or the subject of our task also conforms to the wind conditions. It's up to you. Oh, and you can blame the wind, that's fine, because the wind is going to say, okay, I take the responsibility and you take the pain. So just think about that one. All right, steep approach. Steep approach, and therefore later on we will obviously look at steep approaches. What are the go, no-goes? How do you do it? When will you not be in trouble? And how will it feel? And what will be the experience be? And remember, I've always said that you can read everything that you can ever read, but you cannot learn to fly from reading. I know, huh? Yes, that's right. From reading all the aerodynamic books about spinning, you aren't going to be able to put it positively into a spill and recover successfully the first time. because the dynamics involved in that is going to make your brain stand still. That's why you need good instructors to show you these things. And then obviously when it comes to upset stuff, we don't can practice that all the time. All right. We know the theory, we practice it with a reputable instructor who knows what he's talking about, knows what he's doing, and then, should it happen with us, we've got the ability to recognize and recover.